Hi guys, what we're going to have a look at today is some work that we've already touched on in class a little bit. It's the idea of these complex roots of polynomials. Now I'm just going to put an example or two of the quadratics one for a start, especially for those who aren't too sure about this or may have missed some work in class. So before we have a look at that, just make a note somewhere to the side here of a few basic things about complex numbers that's really important. Okay, so we've seen before this definition: the square root of -1 is equal to the imaginary number I, 1i, and what follows from that, if you square both sides, is that I squared is equal to -1. Now that can be used, for example, if we had the square root of -7, we could replace that with the square root of 7i squared. And so no longer are we going to stop when we get the square root of a negative number. We're going to now proceed using this idea that I can replace the -1 with I squared. So since -7 is equal to 7 times -1, that implies it's equal to 7i squared. And if it's underneath the root symbol, we end up with this. Sorry for that little bit of mess there. Okay, so let's take a look at an example of this for a quadratic. So let's say we had something like -4 minus 3z squared is equal to 5z. Quite often with these complex number equations, instead of x, the variable z is used, but not always. Okay, let's standard procedure here. We're going to make this equal to 0. So I'm going to move the -4 and the -3z squared over to join the 5z, and what we end up with then is 7z squared plus 5z plus 4 is equal to 0. Okay, and now I'm going to use the standard quadratic formula. So negative b would be -5 plus or minus the square root of b squared would be 25 minus 4 times a times c over 2 times a would be 6. Now that is the quadratic formula that I'm using for this. And if you're not too familiar with the quadratic formula, you might need to ask me about it in class or ask your teacher. Okay, so let's proceed. Okay, this is going to be now 25. We need to do the multiplication here first before we do the subtraction. So 4 3s are 12. 12 times 4 is 48. So we're going to end up with 25 take away 48. So the difference between 25 and 48 is going to be equal to 23. So -23 we're going to end up with underneath that root sign. Just made an error there. Of course it's negative. And this all over 6. Now what we've done in the past is said, okay, no real solutions, but now we use our knowledge of complex numbers to proceed. This here can be replaced with 23i squared. And 23 is a prime number, so I'm not going to be able to simplify that root 23, but I can simplify the square root of I squared. So this is equal to -5 plus or minus the square root of 23i. So what am I saying there? 23i squared is the same as root 23 times the square root of I squared. That's one of the basic rules of surds. You can split that up if they're being multiplied here. So that is root 23 times I, or more conveniently written like this. Now let's not forget that's all over 6. Now it is quite common to write the solutions like this as two separate solutions, and we're putting the negative 5 and the root 23 root 23 over 6 times I. So that there is equivalent to that. So what we're saying here again, if I just put that to one side, root 23I over 6 is equivalent to or same as root 23 over 6 times I. And coming back over here, our second solution was negative 5, 6 minus root 23 over 6i. Okay, now sometimes with these roots here of these numbers, you can sometimes simplify that into a simpler surd, and you do end up with some cancellation happening sometimes, but not in this case. Right, let's move on to have a look at a cubic one. Okay, so I'm going to make a new page. Okay, and so we'll have a look at cubics. Remember, they are basically based on y equals x cubed, and then some other terms involving sometimes x squared, x, and a number. So let's take a look at an example of this. So let's say we're asked to solve this x cubed plus x squared plus 3x minus 5 equals 0. We want to find all the different solutions. Sometimes the solutions are also called roots. You see that quite often. Find the solutions, or sometimes they say find all the roots, roots meaning solutions. Okay, so coming back to here, what we're going to do is, like we did when we looked at cubics earlier this year, we'll find one solution using the factor theorem. That is, if I can find a value that when I substitute into the cubic and it gives me 0, I know that that would be a root. And I can see that I've got a negative 5 here, and I can see that I've got a coefficients of 1, 1, and 3. If I can make all of those just equal to a 1, and a 3 and add them together, take away that 5 would give me 0, and I know that will happen if I let x equal 1. Okay, so we'd end up with 1 cubed plus 1 squared plus 3 times 1 minus 5. Yes, that equals 0. Therefore, x minus 1 is a factor, and one of the solutions is 1. But we can also take from that that x minus 1 is a factor. Now what we're going to do, like we did earlier this year, we're going to divide x minus 1 into our cubic to end up with the quadratic. So in other words, we're going to end up with x minus 1 times some sort of quadratic will equal the cubic that we started with. So how do we do that? Well, I'm going to use some synthetic division. Once again, I'm assuming that you know what synthetic division is. If you're not too sure, please ask. Okay, so how do we do that? We take the coefficients of our cubic, we write them down with a bit of space between them, and then we're going to put a little line about here and a vertical line here. This is where our remainder will go, and since this is a factor, we should expect the remainder to be 0. And the other thing we're going to do is, we know that our multiplier is the number that makes a 0. In other words, this number, a 1. So this is our 1, which is our multiplier. So carry the 1 down, multiply 1 by the multiplier, which is just 1, and we now add that, multiply by 1, our multiplier here again, giving 2, add these 2, multiply 5 by 1 gives 5, add, and we get 0. And what the synthetic division should tell us, if we interpret it correctly, is that we now have our cubic is equal to x minus 1 times a quadratic, and these are the coefficients of the quadratic. So x squared plus 2x plus 5 is equal to 0. Now with the work earlier this year, we simply factorized this part here. Now it's pretty obvious, I hope, that we cannot factorize this, okay, not in the normal way. So what we're going to do is we're going to solve this part using the quadratic formula. So x will equal, and using the quadratic formula, negative b plus or minus the square root of b squared would be 4 minus 4 times a times c all over 2 times a, which is 2. So negative 2 plus or minus, right. This is 4 times 1 times 5, that's 20. 16 take away 20 is negative 16. And negative 16 is equal to 16i squared. So let's substitute that. Now 16i squared, that's the square root of 16, which is 4, and the square root of I squared, which is just I. So we end up with negative 2 plus or minus 4i over 2, and this can be simplified, so we should simplify it. Okay, so that's negative 2 over 2. So let's write it just in long form for a moment. And let's just put the plus, minus. That's a bit messy. Let's tidy that up. Four I over 2. Now that simplifies to negative 1. That simplifies to plus and minus 2i. So there's our two different solutions, and yes, if we really wanted to, I'll just put this over here, we could write it as negative 1 plus 2i and negative 1 minus 2i. And I just want you to note that we have a pair of conjugate complex numbers. We have a conjugate pair here, and that is something that, okay, I just want to emphasize right from here that is something that you will always see when you have one complex solution, the other, there will be always another, and it will be its conjugate pair. Not saying that's all the solutions, but it definitely gives you, from one complex solution you can always get another one, which is sometimes parts of all the solutions that you might have. Okay, and here we've got that conjugate pair. So what are all our solutions? Our three solutions are one real solution. So let's put that up here where I've got a bit of room. Our solutions are x equals 1, negative 1 plus 2i, and negative 1 minus 2i. We've got our three solutions. Okay, so yeah, that's an example of solving a cubic, okay, and where we've got some complex roots. Okay, we'll do some further work on that in class, and we'll see you there.